Hi, today I have here with me Ruud van der End. Welcome.
Hi, Alpha. Nice for having me. Thank you for having me.
Cool. Well, I'm glad to have you on. And you're a professor. You do hydrology and also a bit of work with climate. And you look at precipitation recycling, which some people call the small water cycle in the eco field.
Yeah, correct. Yeah, I've been working in this field for I think about 15 years now. Yeah.
Yeah. And so, yeah, and you did this interesting work around, we'll get to this, but just to kind of just to tease what we're going to talk about, you did this work about showing how much evaporation in certain parts of the world then lead to certain precipitation in other parts of the world. So you did a kind of map of
Yeah.
where the rain was coming from and where it's going, kind of.
Yeah, I think in my early work, or probably also kind of my most known papers, I showed some global maps of this process of where well, not only where, but also kind of quantified how much of the evaporation actually comes back to the land surface and how much of the precipitation globally is from land evaporation. And the global number is about 40%, so about 40% of the precipitation we receive is about from land evaporation. Of course, there are now some new estimates, but I think in general that still remains around that number, depending a little bit on methods and data. But I think I was one of the earliest that showed this in a kind of comprehensive overview. Uh, yeah, it
Okay,
was
cool.
a bit of a I don't know. Because as you said in your introduction, I'm a hydrologist. I'm not a meteorologist by training. I kind of call myself also now atmospheric scientist or a climatologist. But this is after 15 years. Like initially, I started doing this research as a hydrologist, so I was, uh, yeah, maybe also rather naive about it. I've seen like the pictures from high school geography where you just see like, oh, hey, what? I mean, probably. I mean, we've all seen this. I suppose in high school geography, where you have a picture, water evaporating from the ocean, it goes to the land that rains down, turns into rivers, and runs off again. This is pretty much kind of the the general view that we have of the hydrological cycle, but
Right.
I think it's a bit more complicated than that.
Right. Okay, cool. So when you were in high school, did you decide to, when you went to college to study hydrology, or was it something different that you first started out in?
Yeah, so when I was in high school, I started with a Bachelor of Science in civil engineering, actually.
Hmm.
I mean, water resources hydrology is also a part of civil engineering, but I think as many civil engineers, they start out with the idea of hey, bridges are cool. Let's let's build those and study those. But I think kind of along the way, I got more and more intrigued, not only by the engineering stuff, but also about like more the how nature works. So yeah, so that's why I kind of shifted towards uh I mean, still within civil engineering, but then my master's with specialization in water resources and hydrology. Yeah,
Okay, cool. And was this at Delft University in the
yeah.
Netherlands?
Delft University of Technology in the Netherlands.
Okay, cool. And
Yeah,
then when you were doing your master's, is that when you first, was that when Savanier, Hubert
yeah. I
Savanier, is
think
that when you
yeah,
met?
Professor Savanaya came kind of into my life.
Oh,
He was a professor in hydrology, and yeah, for people who've met him, very inspiring person, very enthusiastic, full of passion for hydrology and how things work. And yeah, in one of on one of the courses that I took, we had to read papers.
Mm.
I think the majority of the papers we had to read were his own papers, but they were cool papers, so so no problem with that. And he did some work himself in the 90s on moisture recycling in the Sahel, or West Africa, I should say, actually. Um, yeah, but he kind of completely developed also his own approach towards kind of this problem, well, this ground question of where does the rain come from and how much of the evaporation comes back to the land surface. And I mean, there was some work also already before Savanai. I mean, not that he completely invented it, but lots of other studies were kind of looking at, okay, let's just draw a box and try and calculate how much recycles within that box. And he took really a perspective of, let's kind of follow the trajectory of moisture and um, and then calculate, along that trajectory, how much is being recycled. And in his estimates were that, yeah, I mean, rather kind of surprising to me, or really like, yeah, eye opener that in the driest parts of well, I mean, if you kind of go from the coast of West Africa up north, in the drier parts, the amount of precipitation that stems from land sources is actually greatest, which if you see it makes sense, but if you never thought about it, you're like, oh wow, so they have a region, very reliant on rain-fed agriculture, which actually depends for its rain on the upwind region, where also land use is under pressure, and of course, there kind of big implications for water resources. And I think there's also, I remember another paper that we discussed. I think a lot of talk on water resources kind of around that time when he wrote that paper, at least, or maybe people even still do now, is really about, what when people say water resources, they think, okay, how much water is there in how much water is there in the river? How much water can we take out for irrigation? But nobody really talked about, like, I mean, he always said, like, this is all nonsense. Precipitation is the water resource.
Mm.
It's not, if that doesn't end up in your river, it means the water has evaporated, right? So that means it has done something. I mean, it's already been maybe productive for an ecosystem or for crops. And on top of that, that water comes back somewhere else. So yeah, I think that was kind of a very, very kind of inspiring. And I think when he did it in the 90s, like the computational power there was much less than we have today. Also, open data was also much harder to access. I mean, you couldn't access the big climate model data sets, reanalysis data sets that we can access now. So he did it all with analytical equations. And yeah, I think after the 90s, he kind of, yeah, he had this research, but it was kind of on hold, let's say. And I said, yeah, I want to pick up this research for for my master thesis. And yeah, he more or less just said, good luck. Yeah, and I started reading lots of literature, and yeah, from that developed my own model and my own global estimates.
Right. Well, so as I understand it, he's very much his own independent thinker, right? Because he was positioned in Africa during his early days,
Yeah,
and because there was no internet back then, and it was slow to kind of
yeah,
write letters, and it was
true,
too expensive for
true.
phone calls.
Yeah,
He had to figure out everything himself, and so I think later when he was trying to figure out this whole precipitation recycling thing, I think that there was a feeling around that time they just discovered that the sea surface temperature seemed to correlate with the droughts in the Sahel in Africa. And so they thought most of the rainfall was due to the oceans, right? But then I think 70, as I understood, he kind of plotted the amount of rain as you move inland, but the rain didn't go to zero as it would have dropped off to zero if there was no precipitation or recycling. There's no contribution.
Sure, yeah.
So from that,
Now, and
because it didn't go to zero, he said, "Oh, there must be some contribution from land
exactly,
evaporation." Water.
yeah. No, exactly. I mean that I think sometimes, kind of maybe sometimes a blessing, back then when you didn't have access to all the information that is on the internet, you can, spend some more time actually thinking about your own theories and develop your own methods, which is pretty cool. Yeah, but I mean, indeed, as you said, like I mean, at a certain moment, you kind of expect things to go to zero. Well, yeah, of course, kind of we now know that kind of the situation in the Sahel is a little bit more complicated because in his work he really had the Atlantic Ocean as kind of the only water source that he took into account. But I mean, we're talking about analytical equations, right? You cannot make it extremely complicated, of course. Okay, now we actually know that the rainfall in the Sahel, that like even the Mediterranean region, that is one of the most complicated regions actually in the world for kind of recycling, because also the Mediterranean contributes. I mean, not only the Mediterranean Sea, but also kind of the whole region, as well as Eastern Africa, that contribute to uh, the rainfall in the Western Sahel.
Mm.
So, and this is also, I mean, but this is also something, and still, actually, so this is not what Basaf and I found, but this is also something that I found, and I still people find it very difficult to kind of get their head around that there's moisture coming from Europe that could contribute to rainfall in the Sahel, because I think like, oh, but how's it possible that it crosses the Sahara? There is no rainfall there. No, that's true. There is no rainfall there, but there is still moisture in the air, right? I mean,
Right.
I
It
mean,
just doesn't
humidity may
reach
be
the
low, but
humidity.
it still crosses the desert, and that's pretty amazing.
Right. Yeah, it just doesn't reach the dew point so that it rains out.
Exactly.
Crossing. Yeah.
Yeah.
And then I guess I remember reading a paper of his, he was very upset. He was saying that this is such a big deal that the land, if you take down trees, it affects the rain. And
Yeah.
it's such an important transportation system for the water into land. And
Yeah,
yet
I
no
know.
one
Yeah,
was looking at it. We're
I
just
don't
looking
know
at carbon emissions.
I don't know the details of kind of the policies that went on there, but from what I've understood, that there have also been people in the past, advising in World Bank projects, cut down the trees to get more water in your
Mm.
in your river system, and that upset him a lot. And I mean, this would also upset me if I think about it. But I mean, I think those things are not happening anymore. I mean, there are people still cutting down trees, but not with the idea of trying to get more
Increase the
water in
water.
the river.
Right. Well, yeah, well, I don't know. Even in the US, I think there are some farmers who think, oh, we can't plant the trees, they'll take up the water or they'll cut it down. Yeah, I don't know.
Yeah,
There's still some of that thinking.
maybe. So maybe that's still.
So he came up with this idea of quantifying the amount of moisture recycling or precipitation recycling by how much it comes back down on the same continent, right? Because people were trying to measure it in different ways, but he was saying the amount of water that comes up, evapotranspires on the continent that comes back down on the continent is the best way to measure the ratio rather.
Yeah, so then I think there's also been a bit of a metric discussion where, a lot of people are like, okay, well, we just draw a box and we calculate how much recycles within the box. But of course, if within that box, there would be differences between the amount of moisture being recycled, right? So I think that's is that okay? Well, we have to go away from the box. We have to think along I mean, he had lines, but I mean, essentially his point, you have to consider the movement and okay, close to the coast, not a lot of recycling. The further you go inland, the more recycling
Mm,
you get in general. I mean, and that's kind of,
cool.
I mean, that general idea also holds with more complicated global models that I've been running.
Mm. So he was talking about this in class when you were in class, and then did you somehow think, oh, one of these ideas you wanted to take, or what was a stimulus for your research project?
Yeah, it was just the I had the idea that there were lots of, I mean, well, I mean, we read this one paper on the Sahel, and I did a bit of Google searching myself. I mean, a lot of Amazon work also popped up, but I had the feeling that there's kind of the global picture is missing,
Mm,
and yeah, so I kind of wanted to I guess I was just curious. I just
right,
wanted to know what the global picture of moisture recycling looks like.
right.
And that's why I said, okay, I want to pick up this moisture recycling work. And uh, yeah, I mean, I read his papers, but I also read a lot of other literature. I think I had a very unusual approach to the start of my research. Um, or at least, I mean, if I compare it to a lot of students that I have now in my own class, or the kind of students that I see doing their thesis, they spend only sometimes a tiny amount of time on the literature review and want to immediately dive in, do calculations, do things. But I really spend like 2, 3 months just reading.
Mm,
I think, okay, if I want to push the edges of what is known, I should have a complete understanding of what is known about this topic
right.
before diving in, running a model,
So this is for
and
your
can,
master's topic or for your
yeah.
PhD?
What this was for my master's,
Did
but
you
I
think
mean,
it was
this really kind of gradually. I mean, the Dutch system is a bit different than the American system. I mean, in our system, you really have to finish your master's before you could start a PhD. Um, but yeah, for my master thesis, I got such interesting results that yeah, Hubert Savanaye asked me like, okay, I have some funding available. Do you want to turn that? Do you want to turn this into a PhD? And yeah, so eventually, this research, grew a bit, and yeah, I very quickly had my first paper that was of course kind of beneficial from starting
right?
starting already for my master thesis. Yeah, but yeah, then this turned into a PhD also with Hubert Savenay as well. Yeah.
When you're choosing your topic in your master's, right? I mean, you don't want to choose something that's too ambitious because you only have like 1 or 2 years, right? So were you worried that this was a very ambitious topic when you were looking at it?
Um. Yeah. Um. Yeah, I was worried a little bit because especially if you're if you're just reading and okay, but what if things turn out to be more complicated? But yeah, I mean, I also felt that because I mean at that time I didn't have the idea of doing a PhD at all. Actually, I mean that I also had the idea of okay, well. I mean, this is maybe the only time in my life that I have a significant amount of time that I can devote to what drives my own curiosity,
Mm.
right? So that weighed much higher for me than the possibility of of failing an ambitious project.
And did you have to learn some of this climate modeling because you were in hydrology?
Yeah,
Maybe you
for
don't do
sure,
much climate
yeah,
modeling. So you taught
for
yourself
sure.
that, or how did you learn that?
Um, I think kind of along the way. I mean, from reading papers, of course, helps. And I mean, what I did is not was not. I mean, the way I saw it back then, it was more like, okay, I just do a kind of a bookkeeping approach of the atmosphere. I mean, I don't have to even understand all the meteorological processes. It's just grid cells, water goes in and out. Whether this is groundwater or whether this is in the atmosphere, the thing it's the same. Yeah, of course. Well, it's not the same, but but that was really the way I kind of approached the problem back then. And I think when it comes to meteorology, I'm probably still learning today uh, from friends and colleagues in the moisture recycling field that have a kind of more meteorological background, and sometimes I can teach them things about hydrology and the land surface and how those things work. And then you also have other people that have more ecological background who bring other specialty to the table. So yeah, I think you need all those specialties.
Right. So how exactly did you? So you know how much evapotranspiration is happening off the land, how much rain is happening, but how did you figure out where that water went after it evapotranspires to come back down as rain? Do you run a
Yeah.
climatological model, or what is it that exactly that you're doing when you?
Yeah, so what I've been doing, so if people would look at my work is yeah, running we call it kind of a moisture tracking model, but yeah, so the model tracks moisture in the atmosphere, but it's not a model. Well, I think it's a model, but it's all the kind of the what we use is generally I mean in those early papers reanalysis data. So there are that's data based on global weather models that are updated with global observations of the weather. So they kind of provide kind of a best estimate of what we have globally of historical weather, which provides already precipitation, evaporation, humidity, and wind at different levels in the atmosphere. And from that, yeah, kind of just can do yeah, what as I said earlier, kind of a bookkeeping kind of approach, keeping track of what comes in and out. And I think a nice analogy is that of a kind of a die. Yeah, so suppose you have a tank of water and you put a die in there, and this is also what we do in the moisture tracking model. We put a die, but I mean the die is a label that you put there in numerical code, but essentially you put a die and say, okay, I want to know from this specific area where does the water come from. So you kind of color that water in your, or at least kind of that's how you could see it as in an analogy. You label that water and track it through the atmosphere.
Right. Oh, so it is a climate model that you're using that you then plug in the actual data measured and then run it to see where it goes.
In, yes, but I mean it's not a. I think in any kind of in the climate modeling world, is so the tracking happens kind of offline. That how they call it. So offline meaning that okay, well you already have a run of the climate model
Mm-hmm.
that gives you kind of the pure data on the fluxes and the exchanges of the water. And
Mm.
then like I just take out the relevant input and output fluxes, and then in kind of an offline approach, so not running the climate model, but really running only the bookkeeping or the moisture tracking part. We do not alter the total fluxes. We just say, okay, well, we are particularly interested in the precipitation here or the evaporation there, and that is what we kind of track back
Right.
or track forward in time. So we not so there is no alteration of the fluxes. So it's not in that sense, not like a climate model with a kind of a free running climate, but really kind of a bookkeeping approach after the climate model already did its work.
Okay, cool. So what were some of the results you found?
Yeah, so I think the results I found. Well, I'll tell you what the kind of most striking to me was personally was the I think Eastern Asia, China, more specifically. I was kind of okay. Well, China is is close to the coast, so probably they receive most of their rainfall uh, from oceanic sources. But actually, we found that in some specific regions in China, especially like the Tibetan Plateau, like up to 80% of the rain that falls on the Tibetan Plateau comes from evaporation locally or India, the Eurasian continent in general. So that the recycling there was so high was not something that I anticipated beforehand. So, but this was kind of really the surprising part. I think the more relevant part is really the Amazon. So the fact, and I'm not the first one that found this. I think there were several studies before. I mean, maybe I've just shown it in a slightly different way. Um, the case of the Amazon, especially kind of the northern part of the Amazon, providing water for what through atmospheric moisture recycling, providing rainfall for the western part and the southern part of the Amazon, but also uh, even further than that in the big agricultural areas of Brazil, actually rely for a large part of their rainfall on the Amazon,
Mm.
which is uh, yeah, well, I mean, this is probably the the most worrying part. That because we all know the ongoing deforestation, and which is already bad in itself, but a big part of I mean, the whole idea of the deforestation is to increase agricultural productivity there, right? I mean, that's the
Right.
goal of most of the deforestation, but this may actually backfire uh, due to cutting trees, due to less transpiration. This may actually backfire and not. I mean, it's already bad in itself, but it may not even reach. It may not even benefit the agricultural productivity for what it is meant to.
Right. Yeah. Yeah. It's very unfortunate. Um, yeah. So the food production depends on the forest, but they're cutting down the forest to produce more food,
Yeah,
so
to
it doesn't
produce more.
apply.
So it's a negative. Well, it's a positive feedback loop, but it's a very negative story, right?
Yeah. And then it also affects the rain in countries south of Brazil too, right?
Yeah, I think so. Yeah, so also Argentina, Paraguay, Uruguay, yeah,
Mm. And
Colombia. also the west of Brazil. But yeah.
You wrote a paper about rivers, right? Where you're saying that the amount of river flow is affected by land use.
Yeah, yeah, we had there was I think that paper was led by Landwang Erlandsson, my long-term collaborator, who's she's now in Stockholm. But yeah, in that study we compared, we did a kind of a comparison between natural vegetation or uh, what potential vegetation we could have given like no human influence whatsoever compared to the current land use that we have, and see how that affects indeed water resources.
Right.
And there we kind of come back to the issue of, okay, well, if you have like the if you just look at it from without any moisture recycling effect, you see in many cases that the yeah, the change of land use or land degradation, you may even call it, that actually has kind of well, positively impacted the river flows. But if you take into account the moisture recycling feedback as well, it could in the end actually I'm saying this right? No, it doesn't make any sense. If
Wait,
you
are you saying that if you degrade the land, then there's less water transpiring, so then there's less water raining back down on the river? Is that what your paper was saying?
Yeah, okay, yeah, so exactly. Yeah, you're right. So then kind of, yeah, if you just assume, which is what kind of typically happens in many hydrological systems, if you just assume that, okay, we have a here we have a given climate, we have a given precipitation, and we have the natural land use. Oh, sorry, we have the natural land use, and we have, or well, I mean, in a way, we only know the precipitation for the current land use, right? So we have the precipitation for the current land use. So let's compare that to the natural land use situation. Oh, then in the natural land use situation, we would actually have had less water in the atmosphere. But that kind of misses the point that due to the degradation of land, there was less water going up. So the eventual effect may be opposite from not taking the moisture recycling into account at all.
Hmm. Yeah, and that's a big deal, right? Because all around the world, our rivers is what supplies our water to our agriculture and our cities. And so if you can increase
Well,
this,
no, so no.
oh,
So precipitation is supplying the water.
right, right. But I mean, like there's a lot of reservoirs that use river water, is what I mean.
Yeah.
So, but and sometimes,
True. But why do they use the river water? Because the precipitation itself is not sufficient, right?
right, yeah.
So I think that the whole idea of the kind of the the whole focus on river water only comes if precipitation itself is not sufficient, right?
Right,
And if you are in a wet climate where you have precipitation all year round, then I mean there is not much need for irrigation. So
so one of the
I
things we
think
could look
for yeah, the water
right,
managers are really kind of focused on this river flow because you can see it. It's a reliable source. Okay,
right,
true. But I think we have to kind of realize that we only do this because that we cannot rely on the precipitation itself only. But that is in generally kind of the mother of all water resources.
right. So yeah, so one of the ways we can look to increase water for agriculture is actually to look to increase rain
Yeah,
by restoring land.
yeah, I think so. I mean that's yeah. I mean, but then you kind of have the problem is that it's uh, I mean, the question, I mean, if you just look at this from the moisture recycling perspective, the water travels uh, hundreds of or thousands of kilometers. So if you restore land in a particular area, then maybe this benefits other areas, but not necessarily the area itself. It might, but then we may be talking about other processes, maybe surface roughness, harvesting the rain, or some albedo effects, other micrometeorological effects that could potentially, bring more rainfall to a restored patch of land. But if you look at it purely from the budget perspective, the land restoration in one place may actually positively affect other places, which of course uh, makes it complicated because preferably you just have like a project, we do something there, we improve it there, we see the benefit there, and maybe it's not always so straightforward.
Right. Well, that's where transboundary agreements come in, boundary water agreements, where because a lot of rivers already flow through different countries, right?
Yeah.
So they have to make some kind of agreement. But I think there's some researchers now looking at how different countries should make agreements about the atmospheric water too. So
Yeah, true. I mean, I think that's the. I mean, I'm also involved in some of that work, and yeah, well, I suppose that the research community has kind of figured it out that you know that should really happen, but not my specialty. But I would guess that maybe the road to the policy table is still a bit of a long one.
yeah, it's like, well, first people have to even be aware that this is an effect.
Yeah, true. Yeah, and I think more and more people are becoming aware of it. Um, I mean, these things have also uh, been mentioned in. I've seen policy briefs mentioning these things. So I mean, there are people definitely aware of it, but yeah, uh,
You did a paper
I
on
think it
Kenya,
would be great. Sorry?
right? Like you said, I think you said 75% of Kenya's rain or evapotranspiration comes back down in Africa, right? And 15% comes back down in Kenya. So Kenya has some kind of effect on its own rain, but then it has an effect on
Yeah,
Congo and the Tanzania and Uganda, which is
yeah,
downwind from it.
yeah. I mean that's so I mean yes, that happens, but it's I think the people that are more into transboundary water management of rivers, I mean they would probably already affirm that it's already quite hard to make agreements between countries on river flow, and then if you're talking about kind of atmospheric water flow, which is partly an invisible process, it may be hard to have some agreements on there. I mean, my hope is that like big countries like Brazil, China, the United States, where they have they don't really even need this transboundary water management. But if those big countries start realizing it, then this may also trigger. I mean, if they have specific policies on it because they want to keep the atmospheric water cycle functioning, this may also trigger maybe other countries which actually have this the transboundary part as well to also start looking into agreements. But I
Yeah,
mean,
yeah. The U.S. is so big, right? So we in the southwest of the U.S. we have the Colorado River, right? So it's supplying water to 7 different states, and it's a big deal because it's drying up, and but people are not looking at land use affecting rivers there, or through the moisture recycling. So
Yeah, so it's a task for you, I suppose, also to and some other U.S. researchers like Pat Keyes and Francina Dominguez to try and get this on the policy table in the U.S.
right. Uh, yeah, so you worked with Pat Keyes. He's at Colorado, I think, State, and he did work that also shows that there is actually significant. I think he said what 19 out of 29 cities actually, if they restored some of their land use, they affect their local land area affects a third of their precipitation. So there are a number of big cities in the world that actually it still has a bit significant effect even on themselves too. So even without the transboundary stuff.
Yeah, yeah. If you really look at the mega cities, then probably it has an effect. I mean, maybe even more so than just the moisture recycling effect. And I think that, I mean, there is also lots of great work being done on, how cities affect precipitation, but probably also still too little, because there may be other. I mean, cities also emit heat. They have another albedo. So it's not just that they evaporate less moisture. I mean, they have more roughness if they have a lot of high rise. I mean, there are also kind of other aspects that make cities stand out from their environments, which could all affect uh, the rainfall, either positively or negatively in different circumstances.
Mm.
And yeah, I suppose that those things also deserve much more attention. And I mean, there are some great researchers doing great work there, but I think there's still a lot of things to be found out.
All right. When you looked at the U.S., so you found that the rain kind of it's like on the west coast, right? It kind of a lot of it rises, right, and then it evapotranspires, and then it comes back down as rain as you move further to the east,
For the East,
towards
yeah,
the
yeah,
middle,
yeah, yeah, yeah,
middle of the U.S., right? So it falls
yeah,
back. So
yeah.
that's kind of the
Yeah, so
general.
kind of the West, I think it's kind of a combination of the West and the Gulf of Mexico, if I'm still allowed to say that. Yeah, so I think it's kind of those sources, and then kind of they kind of merge together then and go further, propagate further into through moisture recycling, propagate further into the east of the United States.
Yeah. So yeah. So what? Yeah. So like California, what happened in California, Oregon, Seattle, or Washington?
Yeah,
Kind of the land there evapotranspires it back up, right, and then goes to Nevada, Colorado,
yeah.
and then to Midwest. Um, so um, and so what was the percentage you have for the general? Like how much of the land affects the rain approximately in the world?
In the world, so it's about 60% of land evaporation that goes up comes back as precipitation on land.
Okay, so it's actually a bigger contribution than the ocean.
No. So 40% of the precipitation comes from land evaporation,
Oh, 40%. Okay. And
but
60% comes from the
but
ocean.
of but so then about 30% of that becomes runoff.
Uh-huh.
So then 70% comes back into the atmosphere, and of that 70% of the initial rain that fell,
Okay.
60% comes back again.
Okay. So if you see rain on the land, about how much of that started from the ocean without hitting the land first?
If you see rain on the land, so 60% of it roughly came from the ocean. I mean,
Okay.
globally average, right? I mean, so
Right. Okay.
60% came from the ocean, 40% came from from the land. But I mean, as I said before, I mean, there are areas where this can be much higher. So it's not only that. Okay, so you have these hotspots, like uh, Central South America, the east or the center east of the United States, the China, the big part of the West Africa and Sahel, where that number is much higher, right? So then there's really like 60-70% of the rainfall that comes from land-based from moisture recycling.
Mm-hmm.
But I think also the other way around is also interesting, right? So I mean, we're talking about, if we take the US as an example, it's it's like of that initial rain. If you go to the West Coast where you are based, of that original rain that fell, okay, and then part of it runs off, but the part that evaporates back into the atmosphere, the vast majority of that comes back again to the land surface, right? So that's I think the interesting aspect of it as well. So I can even look up the numbers if I'm if I have them here now anyway. Yeah, so yeah, exactly. So I mean, the west coast of the US, it's like about 70% of the water that evaporates there comes back to the land surface. No? So comes back elsewhere in North America.
Mm-hmm. So, because the U.S. is one big, because it's all one country. We can kind of work out agreements between the different states, perhaps. Yeah.
I suppose I suppose yeah.
So okay, so you also did some work with green water planetary boundaries, right? So like
Yeah,
green water is meaning the water that comes from that's passed through vegetation. Is that what green water is?
yeah. So I have to say these definitions with these colors remain sometimes a little bit confusing, but I think I'm in general we indeed speak of green water when it is well, rainfall that uh, comes to the land surface, goes into the root zone, is being taken up by trees without entering a river first or without going to the groundwater first. So those groundwater and river water are kind of considered blue water resources, which you kind of actively, I mean, which people kind of actively also use by means of pumping it out. But the green water resource is rather the part that just happens naturally, right? So just rain that falls and ecosystems or crops relying on that rain-fed agriculture from just taking up water from the root zone.
Mm-hmm. And what's the idea behind it? There's a kind of a tipping point or planetary boundaries around this amount of green water.
Yeah, that's a good question. So I think in as we kind of discussed before, is that I mean we're doing all kind of alterations uh, to the land surface, and if we do too much of it, but of course it's kind of difficult to kind of pinpoint then what is too much. But if we do too much of it, we kind of break down the natural water cycle or the small water cycle as you introduced, as you called it in the beginning. Now, if we change too much of the land surface, we break down that cycle, which may have all kind of unwanted side effects. So if I mean, I think in the Amazon, researchers are in big fear of that there would be some kind of self-reinforcing collapse of the rainforest into a more savanna-like state because of ongoing deforestation, and yeah, then not only destroying those trees locally, but altering the water cycle in such a way that that affects other areas as well, which could then perhaps also not sustain trees anymore, and the negative spiral just continues.
Mm. And what do you think of in places more in the Mediterranean climates like California and Spain, where there's a it's not there's a lot of logging, but there's also these more and more fires, and so that's destroying California's
Mm.
so many fires in the last decade and a half that a significant amount of forests have been destroyed there, and so then that effect of all their transpiration, like it'd be beginning to affect the whole water cycle because
Yeah,
first there was so much logging, but now it's the fires are having almost as big an impact as the logging originally did.
yeah. So then you have the logging, the fires, and all of that probably leads to less infiltrate. Well, when it rains, leads to less infiltration, more runoff, less evaporation. So this may also then affect. Of course, it's kind of sometimes difficult to say how significant it is, but I mean these things build up. So that's why in this green water planetary boundary paper, we also said like, okay, I mean the things we're doing are already, uh, yeah, having such a big impact that we're already crossing that boundary of green water.
And does
And
that apply to, say, just a more local area like California or the Southwest US? It also has a green water kind of tipping point that you need to have that much water moving through trees and vegetation.
yeah, good question. Um, yeah, in a way, it's a kind of a global assessment, but I mean, in the end, it comes down to local or regional areas that are, um, yeah, that end up in such a kind of a negative spiral, uh, yeah, of things. So I mean, as I said, like I mean, it's if you have the logging, then you have the fires, and then and if that then also leads to less rainfall,
Yeah.
either through moisture recycling or to other effects, but in any case leads to less rainfall, then of course that's going to make land surface again more prone to fires.
Mm,
Uh, yeah.
right. Yeah, I just gotta talk about another thing. I was just kind of looking through some of your papers. You also looked at something called the residence time of water in the atmosphere. And so supposedly as global warming, we heat up the air so it holds more water,
Mm.
so now it stays in the air longer. What's the consequences of that with water residence times increasing or water vapor residence time?
Um, you well, the what's the consequence of that? Good question. Um, I mean, I suppose that that in itself is not necessarily uh, problematic. Um, I think the yeah, with climate change. Well, I mean, if the water stays in the atmosphere longer, then it also means that it generally uh, moves further. So uh, yeah, moisture travels a bit further. But I don't know if there is a specific kind of of that specific aspect, the consequence that we
Right.
should
Okay.
necessarily worry about. It's more of an academic exercise, I suppose.
Okay.
That
It's
yeah,
not that
that is what happened. That is what happened. What is happening?
it's not that it stays in the air longer than it has a chance to have more of a greenhouse effect because water itself can absorb the sun.
Mm, um, so I would say, well,
And maybe it's the wrong way to look at it. Maybe,
I'm not. I'm not sure. Maybe not. I mean, this is a little bit beyond my specialty, so
okay.
I rather not comment on that. But
Okay.
I mean, yeah, indeed, that's. I think the more tricky part of it is maybe that mm, because the air is warmer in general,
Hmm.
it also means that you also need more vapor to reach a dew point, right?
Hmm.
So in general, the water cycle holds more vapor. So, but anyway, if it rains at all, sorry about okay. Well, if it rains, then we get more extremes, which we see happening. Um, but also that maybe if you look at it from the moisture recycling perspective, and if you're talking about kind of transboundary water, transboundary atmospheric water management, that water would travel slightly further, but I would say probably trying to establish a method to have transboundary atmospheric water management at all is probably more challenging in the fact that due to climate change, the water moves slightly further.
Mm. Okay. Right. So it takes a while before it comes down.
Yeah.
And is climate change causing bigger, more extreme water events too?
I mean, yes, the climate change is definitely causing more extreme, more extreme water events. I mean, kind of the basic explanation kind of comes from the so-called Clausius-Clapeyron relationship that for every degree Celsius or for every degree Kelvin, the water can approximately hold 7% more water. The atmosphere can hold approximately 7% more water. And because there is more water, there is also more water that can come down. Plus, there is in general more energy in the atmosphere uh, as well. So, I mean, climate change doesn't necessarily explain all extreme events that we see happening around the world, but definitely climate change is a factor in increasing the probability of extreme events happening.
Mm. And what do you think of? So yeah, so the global warming has a big deal to do with this more extreme precipitation event. Do you think land use change there might be any causal link between the land use change and extreme precipitation?
Um, yeah, that's a good question. Um, I'm not sure. I mean, I'm not an expert on that specific part. But so I mean, from the kind of meteorological effect of it, I'm not sure. I mean, if we're talking about the other side of the extremes, right? So if we're talking about droughts,
Hmm.
then probably if we kind of go back to the Amazon or other places in the world with a lot of land degradation. I mean, it it's quite uh, it's a quite logical hypothesis to say, okay, well, that land degradation aggravated the droughts. But if land use also aggravates the wet extremes, I'm not sure. I mean, but if you look at it from a hydrological point of view, but then it kind of has nothing to do with the atmospheric part. Of course, lots of land use changes also increase the runoff coefficient, so they may aggravate floods or things like that.
Mm. Well, one thing that I think that trees do is they create turbulence, right? And so it creates a turbulence up to a kilometer or up the whole boundary layer. So maybe without the trees, the wind can come in, or it's bigger, and so it can blow in more of sudden huge rain.
I mean, I suppose that the trees in general, I mean, even without us having an understanding of all the things that trees do indeed in terms of maybe turbulence, but there are also aerosol emissions. There are all kind of things that trees do. I mean, I think in general they probably tend to smooth out things.
Mm-hmm.
So
You
you
mean
know
buffer variations? Is that what you mean by smooth?
yeah, but yeah, probably they have some kind of tendency to buffer variations to perhaps make extreme wet events slightly less slightly less extreme, to make extreme drought events slightly less extreme
Mm.
uh, as well. But if that is, but I'm very cautious here saying slightly, because it's not that in forested areas that there is no extreme rainfall at all, right? So they still get extreme rainfall. So um, yeah, there is probably some kind of smoothing capacity of forests,
Mm-hmm.
but how big and significant that is, um, uh, is probably still a topic that requires further investigation.
All right. So, so the original paper we're talking about the whole moisture map, right? The moisture recycling map or the small water cycle map of the world. What kind of a reaction did you get from the climate science community or the hydrology community?
Sorry, can you repeat that?
The original paper that you did with when
Yeah.
you masters or and also
Mm.
the moisture recycling, the
Oh,
map of
I
the world.
I, I got lots and lots of I would say overwhelming positive feedback. Um, yeah, from hydrologists saying that, okay, finally somebody is making a case for taking the atmospheric part into account, but also from meteorologists saying that are also have maybe kind of been brought up with this idea of the ocean being the source of everything. So I think overwhelmingly positive feedback, and I know lots of professors worldwide are using these kind of maps in their classes now in universities to provide a bit more insight into the functioning of the global and the continental water cycle. So yeah, that was very satisfying, I would say.
So, do you think you had a ripple effect of a lot of meteorologists and hydrologists now studying this more?
Um, I'm not sure if it was only my doing, but I mean, I think we can definitely say that since since I had my 2010 paper, Origin and Fate of Atmospheric Moisture over Continents, the number of studies studying moisture recycling and various aspects of it yeah, exponentially increased, I would say.
Mm.
Yeah.
And do you think the rest of the climate science community has started to see the importance of it? Like, because the large focus is on carbon emissions and global warming.
Mm.
People realizing that land use and spectrum
Yeah, of
hydrological
course.
cycle is
I
awesome.
suppose as a hydrologist, I'm maybe a little bit biased, but um, I mean sometimes it bothers me a little bit that the I mean if you kind of if you take kind of the climate community as a whole, the well, I would not say the lack of priority that is given to the water cycle at all is sometimes a little bit bothering me. You know, there is so much attention for greenhouse gas emissions, temperatures, but comparatively so little for the land component or the water cycle being even correctly represented in some models. Uh, which is yeah, is a yeah, that sometimes bothers me a little bit, and I wish there was a little bit more attention for trying to build better land models, trying to focus more on not only getting, you know, global temperature predictions right, but also actually predicting the right precipitation patterns at the right place, which is probably a very hard thing to do. So, I mean, lots of respect for all the people that are trying to improve our climate models. Uh, but yeah, I wish there was some more attention to the water cycle.
Mm. And what do you say about our whole land use, like in general, how it's affecting the whole water cycle? Like, what's your general view on that? Like how humans have changed the whole land use patterns, and should we try to restore some of the land, or what's your whole view on this?
Yeah, I think it's well, I mean, in principle, I would say, well, I mean, we also, I mean, yeah, we cannot get around the fact that that there are lots of people on this planet that all have a right to be fed. So so we can never bring back, you know, all land into its original state. So we are also we're also present as human beings, but yeah, I mean, there are also a lot of bad land use practices, uh, like overgrazing or, you know, I think, logging of trees. Yeah, you know, so we can probably do much more and restore degraded land. So, I mean, this probably already makes sense from just livability, biodiversity, prevention of erosion. I mean, there are already lots of great reasons to try and restore land and treat nature respectfully. And then if this has an additional benefit of also restoring parts of the atmospheric water cycle, then I'd say even better, right?
Well, yeah, and then in terms of food, like in the past, we can cut down forests to make farms and all that, but we're reaching a point where if we want our farms to succeed, we actually need more better land use, right? Otherwise, they have less rain and less river water.
Yeah, I suppose. Yeah, uh, true. So, you know, and I mean that again goes a little bit beyond my expertise, but I think there are lots of people doing doing great work with agroforestry practices, things like that, or even forests as food production. So big thing what would help would be uh, to probably have a bit more of a plant-based diet as well. So that would save a lot of food that is now being produced for livestock. If we would simply eat more plant-based, that would already help to be able to restore some of the lands globally.
Right. Cool. And what's next for you? What are you studying next, or some of your projects right now?
Yeah, so one of the things that we're working on, I'm kind of still having still doing a lot of work on my moisture tracking model. We recently did some technical improvements so that it's kind of able to run with again like the newest generation of data. I'm very eager to start working. I mean, there is already a bit of work on moisture recycling in future climates, but I think there's a lot that can still be found out there. And also using maybe my tracking model in a very different way to say something about which climate models have the right processes and where and because of what reason. So I think they're all kind of. So I think I would like to remain or become even more involved in the climate modeling community because kind of as I said, it bothers me a bit sometimes that the water cycle uh, is not getting the attention it deserves. So yeah, I hope to contribute there to give the water cycle and climate models a bit more attention.
Okay, cool. And there's a lot of people in the eco world that are very interested in this whole thing. So if you wanted to connect with some of those people too, it might be good.
Yeah, no, yeah. I mean, I know people. I know people in that world as well. But yeah, I mean, definitely that's uh, yeah, that uh, but in a way, I would say in a way I would say they already know enough, right? I mean, I think there are enough reasons, and moisture recycling is just one of them to to work on ecosystem restoration.
Right.
Um, so I mean, they may not need me to to actually do the project. I mean, they can use my research uh, as an additional argument to do ecosystem restoration. But I'm not sure they actually need me.
Yeah. Okay, well, thank you so much for this very interesting interview.
Thanks, Alpha. It was my pleasure.
Okay, cool. Well, best of luck in your future research.
Okay, thank you.